Hey everyone, welcome to the SledgeCast. This SledgeCast, we're going to be focusing on a LeetCode problem. Um, I'm not sponsored by LeetCode, I just have the free account, and I've been looking at some of these coding problems lately. So what we're going to do today is we're going to kind of work through this merge k-sorted lists problem. Supposedly it's a hard problem, which it may be. We'll look at it. And basically, just go through the description. Merge k-sorted lists, merge k-sorted linked lists and return it as one sorted list, analyze and describe its complexity. So our example here, we have 3 linked lists, and the goal is to produce one linked list that contains all the elements. And then here they have our, we'll start a solution in Java. I'm doing most of these problems in Java right now. But there's other options as well. Let's see if we have Go. Yeah, so we have Go as well. And this is, they basically just implemented their own linked list of ints. It's all pretty similar. The goal of this problem is to deal with, well, I don't know what the goal, but you want to deal with your own linked list structure and not use the standard library, I guess. So just to look at this again, all of our linked lists are sorted, but what it doesn't look like is our lists are monotonically increasing. So this list starts at 1, goes to 3, goes to 4, goes to 5. This list starts at 2 and then goes to 6. What I haven't seen, there's no rule though that we can't have like a list that goes from 7 to 10 and the list that goes from like 1 to 5 here. So one of my initial thoughts when I was looking at this was, why don't we go through, like, iterate for the lists and just pop off the first item, stuff in another list, etc. That would give us one long list. The issue though is that not the lists themselves are not sorted relative to each other. So we just go in, we pop some stuff off. Let's see, we go here. So let's pull this in here. Let's put my example in instead of this other thing. Alright, so we got this. Let's say we have another entry here, which is 8 to 10 to 15. Alright, so now, well, if we just pop the first item off, we get 1, 1, I guess we can do these little arrows. 1, 2, 8, 4, and then 3, and then dot dot dot, I guess. Well, this is not a sorted list now, where we had some sorted short lists, now we have one sorted, unsorted big list. So at this point, I'm not really sure if there's a hack to this, to like get this in an ON time. But if you think about it, let's say we don't know any tricky hacks, and all we do is take the full, if we just merge these together and then sort them, what is our time complexity here? Well, typically, making all these lists together is going to be an ON operation. Basically, appending lists, list insert is O of n, or actually O of 1, really. Insert is O of 1, because basically you just add another item on the end of your list, and then you're done. It's pretty quick, it doesn't take too long, and you just get right to it. So the whole thing is appending all these lists together. So appending m lists with n elements is O of n. So that's pretty simple. So we do that. That means our base is O of n already, and then we're going to add our sort. Because we also have to sort things. We appended the lists. That gives us an unsorted list. So now we sort it. Okay. sorts. We have several big sorts, and by big I mean like there's a standard sort. So there's Quicksort, merge sort, and heap sort. There's a couple other sorts as well that people use sometimes, like bubble sort or insertion sort. Those aren't really commonly used in like standard libraries and things. Quicksort is big for in-place sorts. Heap sort and merge sort can be pretty useful as well. But these are all essentially O of n log n sorts. It's just how the sorting algorithms go. That would give us a solution of O n plus O of n log n, like this. And this is just a multiplication here. That looks worse. Alright. And then since we're doing like maximum big O notation is always like the biggest or the worst case. So basically this term, the on, is not going to expand as big as on log n because this is expanding as well. So you can basically summarize this to roughly O of n log n. So this gives us kind of like an upper bound on what our complexity can be for this problem, because you can pretty naively solve it just with appending things and then doing a sort. So what I did next at this point is I just did a quick look at Quicksort, because basically we know that our sublists are already sorted, and if we look at these Quicksort, merge sort, heap sort, etc., they all do it slightly differently, and one of them might be better for a problem than others. So like Quicksort works by you have one list or one array, you choose a pivot, you compare the two sides, you move things around. So that's kind of how Quicksort works. Merge sort is basically you merge things together, you break up your array, you merge subpieces together in a sorted manner, and then you work your way back up. Heap sort kind of works based on a principle of a heap, where you insert things into a heap and then they get sorted like that. So just looking at Quicksort earlier today when I was preparing for this, because I wanted to see if there was basically if Quicksort had an advantage when you had sorted sublists. And I was just kind of scanning through here. I was on my phone, so the formatting was a little different. But yeah, we got all sorts of good stuff. Choice repeated, optimizations, parallelizations. I think I was looking at the formal analysis section, or I was looking at the comparison section. But basically, yeah, relation to other algorithms. So this is where you can get some good, basically comparisons. So Quicksort is basically the space optimized version of the binary tree sort. So you basically, instead of using an actual tree, you use a recursive tree. And the recursive tree is in place. But this is just for Quicksort. And then also for Quicksort, it's not normally a stable sort. It's easier to write it without it being stable. So it makes it harder to sort things without being careful. Cool. Alright, yeah, so Quicksort also competes with merge sort, another algorithm. Yeah, so this is a line that caught my eye actually. So I'm just doing research. Merge sort is a stable sort, unlike standard in-place Quicksort, heap sort, and can be easily adapted to operate on linked lists and very large lists stored on slow to access media. So our problem is dealing with linked lists. So that makes me think maybe merge sort would be a good fit for this because it's good with linked lists. I mean, kind of the reason I was looking at different ones is basically because we have these sorted sublists. So if we can just combine them in a convenient way, it'll be pretty quick. All right, to merge sort. So yeah, basically merge sort, we got some implementations here. I'm looking for a little diagram. There's gotta be one here. Yeah, here we go. Let's wait for this to render. Okay, so basically, here's kind of an overview of what you do for merge sort. You start with your array, you break it down into smaller ones, then you break it down even smaller ones, then you break it down into individual elements, and then you say, okay, I got two unsorted elements, 38 and 27. Which one goes on the left? Which one goes on the right? Well, 27 goes on the left, 38 goes on the right. You do the same thing for different groups. 10 by itself here, it just goes by itself. So then we have 27, 38, 343, and 9, 8, 82. Well, you gotta merge these together now. And basically, let's say 27 and 38, they go next to each other. 3 and 43 go on the ends. Alright, great. 9, 82, and 10. 10 goes in the middle. So I need to figure out what the details of the merging steps are. But just to start us off, this looks kind of similar to our scenario because we have all these smaller arrays already. We already have a bunch of these. We just got to break them down the rest of the way and then figure out how we're going to do this merging here. So let's review that. Just look at the algorithm. Yeah, so we got this point here. All right, divide the unsorted list into n sublists, each containing one element. Repeatedly merge sublists to produce new sorted sublists until there's only one sublist remaining. This will be the sorted list. Okay, that's interesting. Because we already have sorted sublists. So this first step, divide the unsorted list into n sublists, each containing one element. Okay, that's not too bad. But this here, repeatedly merge sublists to produce new sorted sublists. We already have sorted sublists. So that means I think we can just skip. I think it means we can skip the whole first phase. Like looking back at this, if we already have sorted sublists, that means we're basically starting here at this merging phase where we're merging our little lists together. And that could actually save us a lot of time because we don't have to break this up. We don't have to merge these short lists because we already have a bunch of longer lists. My question then is, what is the variance in the lengths of our lists? Merge k sorted linked lists and return as one sorted list. So it doesn't really say that. What the sizes are? I don't know if that'll be an issue or not. Alright, so let's go back up here. I want to know how to merge my lists. Alright, so they got a bunch of different options for doing merge sort. Sorry, I'm reading this. Top-down implementation. Example C-like code using indices for top-down merge sort algorithm that recursively splits the list called n, called runs in this example into sublists until sublist size is 1, then merges those sublists to produce a sorted list. Interesting, alternating the direction. So I really only want to merge sorted lists. So let's see where we go. So top-down split merge. Sort the given run of array A using array B as a source. And this is just some weird. So what'll happen a lot is the CS people, the computer science PhDs or whatever, they like to feel like they're math people. So they'll use mathy notations, which often is really useful for them, but no one else does that shit. So there's this gap of understanding. If you're naming things like this and you submitted a pull request to me, I would tell you to rename all of your variables because they're retarded. Like index, I guess this is index begin, index middle, index end. It's not really horrible, but no one does this. Anyway, I want to see how to merge things. Alright, okay, and the left run head exists and is less than or equal to the right run head. How are they merging? I would have really appreciated a more clear explanation of how we're merging things. And it's probably something that's pretty obvious, so maybe I'm just a big dummy. Alright. Another example of why you want your arguments to your functions to be typed, because I guess these are ints and these are arrays that we're sorting. So we have A, B, left, right, and end. Alright, so now we have some pseudocode. Alright, okay, here we go, we got a merge function now. Okay, left, right. So we have two, presumably, arrays or lists. We're creating a new list. Well, left is not empty and right is not empty. Okay, so we're just doing comparison. So basically, we have two linked lists. They're both sorted. So we compare the first two elements. The bigger one goes on the left. The next one, I think, just stays where it is. And then you compare the next two heads until you're done. So while left is not empty, if first of the left is less than or equal to the first of the right, then append the first of the left to the result. Left equals rest of left. So you basically pop the first entry off of the left array if it's smaller or equal to the one on the right array. If otherwise, if the left one is bigger, then you take the one on the right array and pop that one out. And then you do that as long as there's anything left. Okay, yep. So this runs as long as we both have entries in both arrays. And then they have these two while loops for just to feed out the rest because it's sorted and it's going to go in there anyway. So this is basically the bottom half of the merge sort. And I think this is really all we need to figure out what we want to do, except for maybe making this a little bit more recursive and applying it to our linked lists and getting some of the coordination going. But yeah, I think this is literally half of this algorithm is all we need here. So let's do a bit of coding. Okay. So let's write a merge function. We got the solution class, and we got one method here. I'm just gonna make a. It doesn't have to be public. This is gonna be a private method. Merge lists. I'm gonna make this merge sorted list. Alright, merge sorted lists, and we take list node left. Come on, list node right. And these list nodes are really just the root nodes of our very basic linked list implementation here. Just got to be aware that we don't know how long the linked list is. We don't know how how long it is. We don't have a lot of operations. We have to do a lot of stuff manually. But we got a couple steps here. So first step, basically while both lists have entries, both lists have entries, compare and insert them. So this is one thing that happens with LeetCode that is super confusing to me, but it basically like slows down so much. I'm gonna refresh the page. So it's possible they have like a memory leak in their JavaScript or something. I don't know what it is. Then my computer's also running hot because I'm running QuickTime to record this. It's kind of an expensive operation. I only run the smaller 13-inch MacBook, so it doesn't have as much power. But shouldn't really interrupt us. Insert them based on which is bigger. Okay. So let me think here. So left and right, but basically what we want to do is while so we want to say both of them still have entries. So while left dot next is not equal to null, and we're going to do and right dot next is not equal to null. This does do one little bit that we're going to have to take into consideration. I'm going to make this recursive. So this merge method is going to recursively, does it really mean recursive? I've got to iterate through this somehow. And I don't really have iterators, so recursion works. I can also change my my pointer index, like something like this. So you do list node right index equals what right list node left index equals left. So this is basically going to be a pointer to whatever our active index in the actual array is. So this just lets me iterate my pointers a little bit. Okay, I'm going to change the order because I'm doing left right, not right left. Alright. So now what we can do is basically compare. So as long as we have more things after this, so while there's more entries, that doesn't tell me if we, anyway, we'll start here. I'm a little bit concerned about what do we do when there's one entry left in one of them, or two of them. What if they both have one entry left? Well, we want to iterate this loop. So, because right now this will end when we have one left in each. I guess we can look back at this pseudocode here. So they're doing while left is not empty and right is not empty. Whereas what we're doing is while left has more elements and right has more elements than our current index. So basically, my last element. I guess I can just hard code it after this loop. It's probably the easiest way, to be honest. Yeah, so let's just move forward and we can capture that edge case later. Alright. So basically now we've got that if statement, if left index. Now let's look up here. I'm gonna delete some of my notes. Yeah, it's dot value. So left index dot value is less than or equal to dot value. All right, the left index is less. Okay, cool. That means it's going to be the first node in our new list. But we've got to add it now. Yep, so yeah, so basically if it's less, add first of left, add node to new list. So let's just quickly create a new list. So we've got list node, merged equals null. All right. So then here we're going to do if merged is not equal to null, so if merge is not equal to null, that means we already have a first element. So what we're going to do is merge.append basically. So what we need is a append method to a node. So I'm just going to write one because I don't want to have it be messy in here. Private append append, yeah. And what we're going to return is a list node. So that's just going to be the first node. This is going to be, so we got list node first, and then we're going to have list node new, and this is our new node. New node. All right. So yeah, so basically what we have to do is take our first node, exhaust its pointers, iterate along through it, and then add this guy to the end. Append is just adding to the end. So we're going to do this null check here. If first is first equals, oops, so we're going to null equals first. This is a thing professionals do. That's not really necessary, it's just convenient sometimes. Basically, you can't assign a value to null, so you're never going to accidentally set null equal to first. What we could do is accidentally do first equals null, and that's probably not what you want to happen, so reversing it helps sometimes. So if null is equal to first, then what we can do is first equals new node, and then we're done. Boom, amazing. So at the bottom here, we're going to do return first. All right, great. And technically, this could be a void method if we go into just modify first, which we are doing. And often you will make it, because this doesn't really, this can just be void. All right. So yeah, if null equals goes first, great. Otherwise, while we're gonna have to do an index again. So we're gonna have list node index equals first. Cool. All index dot next is not equal to null. Index equal index dot next. So basically, as long as index dot next is not null, we're gonna set index to be equal its own next. That'll give us the last entry, and then what we can do is we can do index.next equals new node. And then I think we're basically done for this. Amazing. Great. Now let's do that. I don't like to have code line up against these braces. Alright, so now we can use this append method over here, and it will solve the problem of having to do a bunch of if statements. And so we can do append, then we can do merge. Even though merge is null, we have that check here. We're already checking for null in our append method, so we don't have to think about it. Sometimes you're not always going to want to do it like this. I'm mainly doing it like that because I don't want to check for nulls in my iteration here, and because it's just for the first case. But you can also just do an if statement and grab that one. But I would have to do the first two indices outside of my while, which I don't want to do. So that's how we end up with this. So we merged. Which node are we adding? If the left index.value is less than the right index.value, we want to add the left node. Add left node to new list. So we're going to do here, we're going to do left index. I'm wondering if I need to, I should probably create a new one. So we can do new list node of left index.value. I think that's a constructor. Yeah. Great. So we're just appending a totally new node. That's equivalent to the old node. Okay, good. So then we have an else. Oh, and we do have to do one other thing. We now have to say left index dot next. Or sorry, left index equals left index dot next. Because we've basically used up that node, we don't need it anymore. We're not going to insert it again, so we're done here. So let's go into our else. This is add right node to new list. How this get indented? And why am I getting a phone call?